Thank you very much, Helen. We had a very exciting day yesterday. Lots of, I think, new knowledge from all over the places, covering different parts of the electromagnetic field. I think it as a first day, it was a little bit tough with lots of knowledge on chemometrics, X-ray, terahertz. But this is what I think we need in order to combine all the knowledge in our heads and try to find consistency and work them for understanding of water. Let me open up our session on. We decided to call it basic science because I think we, in this session, we will be able to understand new, understanding new phenomena. And my pleasure is to introduce Professor Hamaguchi, Hiroo Hamaguchi. He was professor at Tokyo University. Also, 8 years ago, he, in his group, wrote a paper on using Raman spectroscopy for understanding the water in the cell, in organella. And today he's going to talk about a new discovery, and I'm really, really thrilled and looking forward. Please, Professor Hamaguchi.
Thank you very much. Good morning. It's my great pleasure to see many new friends in this, to me, new field of aquaphotomics. My background is spectroscopy, and in particular, Raman spectroscopy. And today, I'm talking about application of Raman spectroscopy to water. And this work has been done with my former students at the University of Tokyo, and also the postdocs at Jiaotong Dashi in Taiwan. First of all, I have to thank Senkoba Sensei for a very nice introduction to this community. And the work has been published June this year, half a year ago. And I first sent this paper to Nature, but they rejected on the spot. So I hope that they will regret in the future that they have declined this paper. Anyway, I had a lot of difficulty in writing up the introduction of this paper because my knowledge on water and related things were lacking, obviously. I still feel that my knowledge on water is very, very limited. So this is a really nice occasion for me to get your feedback on the work that I'm showing to you. So this is, everyone knows about this. So no need to tell anything about that. Then Raman spectroscopy. I'm sure all of you know about Raman spectroscopy, but I have to tell one thing. It has anti-Stokes and Stokes Raman scattering. The intensity ratio of the Stokes and anti-Stokes Raman lines gives you the temperature of the system. Okay? So you do not need to have a thermometer to measure the temperature, but you can determine the temperature by the Raman measurement itself. And then this is my supervisor. 40, 50 years ago, I learned from Professor Shimanouchi that spectra letters from molecules, very, very romantic, things, and vibrational spectra, molecular fingerprints. So we want to read the molecular fingerprints. So I would like to read spectra. Okay? So there are many approaches to analyze spectra, but I prefer spectra to loadings. Okay? I want to see the spectra. This is my basic standpoint. So now the apparatus, very briefly, we measure milky water in capillary, and we use 532 nanometer laser for excitation. We have two spectrometers separately measuring low frequency region and high frequency region. And in the low frequency region, not only Stokes, but we also measure anti-Stokes to know the temperature of the system. And then, of course, low frequency region, we have the intermolecular hydrogen bonded vibration. We expect that, intermolecular vibrations. Of course, high frequency region, we see the OH threatening region. We measure separately the two regions of the Raman scattering. So this is how the temperature changes with time, starting from 15 minutes to about 200 minutes. We gradually cool down the system. These are pictures. A is here, it's 40 degrees, and then B is here, about 0 degrees, still liquid, and some C here, so minus 20 degrees, still liquid. So here we have the cold water, we have super cold water, this is room temperature water, and we checked that there is no crystallization occurring in the experiment. And we measure the temperature by Stokes and by Stokes ratio, so that the result is here. So we use the temperature which we measure by Raman scattering. So in many measurements, it's not easy to measure the real temperature in the part of your sample where you look at by spectroscopy. But in this case, we are using the same laser beam, same Raman scattering to measure temperature, that we are sure that we are looking at the temperature of the sample where we measure Raman scattering from. Then we got this nice 140 temperature-dependent Raman spectra in the range of minus 23 to 45 degrees. This is just an ordinary thing. But we did the experiment very carefully. How we do analyze that? The first one, we use two chemometrics method. The first one is a well-known MCR analysis, which the principle was already well established, but some people are also mentioning this yesterday. But we use next one, new chemometrics, which we developed a few years ago. And this is called HAMAND, hypothetical addition multivariate analysis with numerical differentiation. And actually this software is patented in the United States and in Japan. And I'll show you later the principle of HAMAND. Now, here I show you the Raman spectral liquid water in separately between 15 degrees to 45 degrees, and the whole temperature range from minus 20 to 45 degrees. If you look at in this range, you see very nice isoscattering point. That is equivalent to the isosbestic point in absorption spectra. And yesterday, a few people showed very nice isosbestic points in water in this temperature range. That means in this temperature range, the system is a two-component system. But if you go to lower temperature, then this isoscattering point is lost. That means there are more components contributing in this temperature region. So we first analyze this temperature range by MCRR's analysis. So we use MCRR's analysis. So we want to analyze many spectra in terms of a small number of principal spectral components. And then we want to express all the observed spectra in terms of the linear combinations of some component spectra. This is the principle of MCRR's analysis. And first we do what we call singular value decomposition, and then we know how many principal components are there existing in the system. So in this case, 1, 2, 3, 4, 5, 6 principal components should be meaningful. And all the others are not easy to make distinction from noise. So in this case, we select only 6 components. And then we go to similar matrix factorization, assuming that all the components are positive. And we do this kind of factorization using a small number of principal components. For example, if we have 1,000 spectra here, but we only use, say, 6 components to separate, to make the whole spectrum in terms of only 6 spectra like this. So this is very well established already, so many of you know this. And we can just use this one. This is the same figure. And we first concentrate on this temperature region where we know that the system is a 2-component system. Then we do this singular value decomposition. So here are singular values first, second, and then the following one are very close to noise. This is the temperature dependence. One is constant temperature dependence like that. So we see that these 2 components are the principal components of the system. And then we do the MCRR analysis. Then this is the result. So we have 2 components, I call it A and B, in temperature range 15 to 45 degrees. And this is very consistent with the existing analysis of, say, near-infrared or whatever the other spectroscopy. So in our case, in addition to this OH stretching region, we have the low wave number region, starting from 40 wave numbers to 400 wave numbers. So our Raman can very nicely detect the low wave number region. Some people call it terahertz region, but we stick to a low wave number region. And we see very nice features here only for component B, and not for the component A. That means there are 2 components of water structure in this temperature range. One has got a very clear structure, and many people argue that this peak is a tetrahedral stretching, hydrogen bond stretching motion, and this is hydrogen bond bending vibration. There are many discussions about this. But at the same time, if you look at the higher wave number region, you notice that, these are both hydrogen bonded. This wave number is about 3,500. This is obviously hydrogen bonded. So there is no hydrogen bonded water here. So hydrogen bonded, both hydrogen bonded, but one with structure and the other without structure. So we call the component A destructured hydrogen bonded water, and B the structured hydrogen bonded water. Okay? But this is really consistent with existing analysis of the 2-component system. And this is the temperature dependence. And if we plot this temperature dependence, we very nice straight line. I was very surprised to get this straight line. This is purely experimentally obtained. From that, we have the value of enthalpy difference between A and B as this number. And then if we know the enthalpy difference, we can predict the ratio of A and B in the lower temperature region. Here we observe A and B, but we can extrapolate the spectra like this with a known enthalpy difference. It's easy to predict the ratio of A and B at any temperature. Okay? So please remember this. Now, if we include all that low temperature in the low temperature region, then singular value decomposition gives 1, 2, 3, 4, many components. It's not easy to say only 2 or 3 components existing there. So what can we do? So what we did was to use HAMAND. HAMAND is an abbreviation of hypothetical addition, multivariate analysis with numerical differentiation. And this was already published in a paper here and patented. This is a kind of numerical standard addition method. But in the usual standard addition method, you need to prepare and measure many samples with known concentration added samples. But in the case of HAMAND, we do not need that. We hypothetically do the addition numerically. So we do first hypothetical addition, then we got a derivative spectra to remove the effect of background, and then MCR analysis, matrix decomposition, and then spectral decomposition. I show you the flowchart of HAMAND. So here, black is the observed spectrum, and we add hypothetically known target spectrum with different coefficients. So we produce, for example, 1,000 spectra with different 1,000 coefficients. So we got 1,001 spectra like this. And then we do the numerical differentiation. Then we use the multivariate analysis, assuming that this is a two-component system. The one component is constant over the added concentration. The other is linear to the added concentration. It is obvious for 1,000 artificially produced spectrum, this is constant and this is linear combination. The remaining one, that is observed spectrum, should be on somewhere here. But this line does not cross the original point because there is some extra concentration already existing in the sample. So this is a standard addition method, the same principle. And then from this we can tell the spectral decomposition like this. So black is a linear combination of blue, red one, this is residual spectrum, this is a component spectrum, target spectrum. So I show you how HAMAND can work. This is the urine Raman spectroscopy. So first, the black one is a urine spectrum, and then this is urea spectrum. By using HAMAND, if you subtract this urea spectrum from the black, then you get this one. So you see this peak disappears, okay? So this is the first residual spectrum after the reduction of elimination of urine. And then you do the same thing for sulfate. So here we have the sulfate, it is eliminated, and then bicarbonate. It's not easy to see bicarbonate, but very, very small peak. You cannot easily see by your naked eye, but HAMAND can see it. And then carbonate like that. Then we have the remaining. Still we have some feature there, and HAMAND can assign this. So these are the creatinine, nitrate, and monophosphate and diphosphate. This kind of subtraction we can do. So HAMAND can be used in many ways. One thing is to determine the concentration in your sample. The other, to eliminate the known spectra and look at the residual. So whatever the residual is, you can do the subtraction of your target spectrum from your complex overlapping spectra. So we use HAMAND for our water study. So as I showed you, so here we have the observed spectra, but we can extrapolate the A plus B contribution to lower temperature. So we subtract these spectra from the observed spectra of water in the low temperature. So if we do that 268 Kelvin, then the spectra is so. The linear combination A plus B and C is the third component. And here, the X coefficient is 0.961. That means almost all, this is observed is black, and this is violet is A plus B, and C is the remaining. So most of the spectra are from A plus B at this temperature, 268 Kelvin. But If you do it at 251 Kelvin, then this is observed, and this is A plus B, and you have the remaining C like this. It seems there are meaningful features remaining there. And we do this analysis for all the temperatures, then we get this one. So at 0 degrees, there is only small residual, but it grows up like this. And that means the third component, its contribution is increases with decrease in temperature like this. And at minus 23 degrees, it's just very nicely featured like this. So the results so far, we have 3 components. The first component A is the destructured hydrogen bonded water, and B is the structured hydrogen bonded water, and C, what is C? I'll give you the answer. This is the nano-ice that I'm going to discuss. But you can see the spectrum somehow look like ice. Okay? Then HAMAND determines the coefficient of contribution A plus B. The coefficient is almost unity until about 280 degrees, so 10 degrees here. So above 10 degrees, it's almost unity. That means that it's all A plus B contribution. But if you go down to say minus 250 degrees, then it goes down to 0.9. That means 10% of the spectra are due to from the third component. So we know the ratio A plus B and C. And if we plot this number, this is the ratio of A plus B and C, and extrapolate to make it 0. That means x equal 1. Then it crosses the point at 230 degrees. So A plus B is liquid water. I give you the answer. C is a kind of crystalline water. Then the ratio is 1 to 1 at 230 degrees, plus minus 10 Kelvin from our experiment. That agrees very nicely with a known homogeneous nucleation temperature of ice. And we also discussed the volume of liquid water as estimated from HAMAND determined coefficient. We know this coefficient, then we extrapolate the volume of A plus B from the norm. This is norm curve here, and then we extrapolate this curve like this. And then we assume the volume of ice, IH, for the third component. Then we have the volume from A plus B and C like this, a simple equation. And then we calculate the volume like this. Okay, we got this nice curve. And if we invert this result, we make the density, and density nicely makes a maximum at 4 degrees. This is what's known as the density maximum anomaly water. So our analysis nicely reproduces the maximum of the density of water in the liquid phase at about 4 degrees. Now, to summarize, our Raman hyperspectral analysis has shown that there are 3 components Raman detect in water, and in room temperature water, we have 2 structures. One is destructured hydrogen bonded water. I'm not sure whether this naming is a good one or not, but that means there is no structure, maybe fragmentary hydrogen bonded, and it contains many different structures. So the spectrum is the average of many different fragmentary hydrogen bonded water. And form B is a structured hydrogen bonded water, and we tend to think this is just a tetrahedrally coordinated structure that is argued by many researchers. And then the third one, that becomes contributing in low temperature below 10 degrees. So be sure this is above 0 degrees. Okay, it's not supercooled water. So even say 5 degrees water contains this nano-ice. So what can we say? Can we call cold water a liquid? So we all taught in schools that above 100 degrees water is vapor, between 0 degrees and 100 degrees it's liquid, and below 0 degrees it's crystalline or solid. But actually, I discussed in the same way in the research of ionic liquids, maybe 15 years ago, 10 years ago. I also claimed that ionic liquid is not a liquid, it's a structured liquid. So I think we need many more discussions to understand the nature of water, cold water. So this is the story. And I'm adding one thing. This is still a preliminary stage, but we are now trying to explain the spectrum we obtained for component C, nano-ice, by what we call the Phonon confinement effect. So in Raman scattering, in the ideal crystalline, because of the momentum reservation, only the points in the dispersion of zone center, dispersion space zone center is active. Okay? So k equals 0 point can give a rise to Raman scattering. But if your size is smaller, nanometer scale, then the k equals 0 selection rule breaks down. And then non-k not equal 0 point contribute to the Raman scattering, and then it makes the shift of the peak position and broadening the spectrum. So we do simulation with this Phonon confinement simulation, and this is the result. So this is ice, this is a PCM simulation, and form C, if we assume 2 nanometer confinement size, then it's nicely, reproduced this one. And in addition to that, form B spectrum, that the structured hydrogen bond water spectrum, can also be well reproduced by 1 unit cell confinement. That means the fundamental structure of ice, that is tetrahedrally coordinated water. So from that, we discussed that form B, structured hydrogen bonded water, has got the fundamental structure very similar to the unit cell of ice. So this is about water itself, and I briefly show you this result, which published not 10 years ago, 5 years ago, sorry about it. And we studied living cell by Raman spectroscopy, and we studied many things, including water. And here I show you the water spectra and cell wall, mitochondria, nucleus, lipid droplet, and here the spatial distribution. And this spatial distribution is the same as that of mitochondria, nucleus, and lipid. So depending on which organella the water belongs to, the spectrum changes like this. This is ordinary water. So if you go to, say, a lipid droplet or nucleus, then this peak becomes, a little weaker. Okay? So here I know that in this room temperature range, we have structured hydrogen bonded water and this structured hydrogen bonded water. So in the case of nucleus and lipid droplet, maybe structured hydrogen bonded water contribution is less, smaller than this structure. But this is all data, and we are planning to examine more in detail of the organelle-specific water in living cells. This is one only example. And finally, I want to add one thing. This is Hyper-Raman scattering. So Hyper-Raman scattering is further complication of Raman scattering. In Raman scattering, we have one photon disappears and one photon appears. But in the case of Hyper-Raman scattering, two photons disappears and one photon disappears with a shift of vibrational frequency, which is called Hyper-Raman scattering. So we are doing Hyper-Raman spectroscopy for a long time, and very recently found that the Hyper-Raman of water is very, very interesting. And here I show you, this is Raman spectrum, infrared spectrum, or stretch or bending. Here we have the intermolecular bands, but somehow in Hyper-Raman scattering, these intermolecular bands are very, very strong. And we already analyzed this spectrum, and also we made the effect of addition of salts to water by Hyper-Raman spectroscopy. And this region changes drastically. So this study is still in a preliminary stage, but I can tell you that Hyper-Raman will also be useful in aquaphotomics studies. So at ambient temperatures, liquid water consists of two forms, structured hydrogen bonded and destructured hydrogen water. And nano-ice formed in cold water below 10 degrees and causes a density maximum anomaly. The size of nano-ice is most probably 2 to 4 nanometers. So cold water may not be a genuine liquid. And I would like to say that Raman and Hyper-Raman spectroscopy will play central roles in future aquaphotomics. Thank you very much for your attention.
Thank you so much for very elegant and very informative presentation. Really, thank you. Question, Jerry?
In support of your observation of nano-ice, various people have found, during the process of cooling the water toward freezing, various people in the process of lowering the temperature toward freezing, various people, including us, have seen something called feathery ice. I'm not sure if you're, there are a couple of different descriptors of this. And you can see in the optical microscope structures that look like small pockets of ice. It's not ice, but it has structure to it, and it occurs only as you're lowering the temperature toward freezing. So I wonder if this is additional evidence for your suggestion of nano-ice.
I have a few reasons why we identify its ice. One, we assume the density of ice for calculating the density, and it nicely reproduces the maximum. Okay? The second one is the spectrum can be very nicely explained by the Phonon confinement model. Phonon confinement model starts from ice. Then you can reduce the size of the coherence and then come to the spectra, which are very close to what we observed for nano-ice. Okay? Maybe the third one is if we extrapolate A plus B, the ratio of A plus B and C, then it reaches to the point the temperature there agrees with the known homogeneous nucleation temperature of ice. So there are three reasons why we think that it is ice.
Thank you.
I have two questions. Mr. Hamaguchi, do you think that your explanation on the basis of nano-ice is a reliable, complete explanation, qualitative explanation of the strange behavior of the water in the temperature interval 0-4? Because you said below the 10 degrees cause density maximum, but the maximum anomalies is only in this interval. What does that mean below 10 degrees? Second question, about Phonon confinement. From the quantum point of view, Phonon is very unstable formation. confinement, in fact, in physics, means something stable. That these two notions combined is some strange combination. Can you explain more detail about this?
Thank you for the questions. And the first one, we use all the data observed, not only the data below 10 degrees, to reproduce the whole curve, temperature dependence of volume, okay? And eventually makes a maximum here. So we are not restricting temperature range below 10, but we use all data from 320 to 250 to produce the whole curve here, and eventually this makes the maximum or minimum here. So this is my first answer. The second answer, I understand that there are many discussions about the phonon confinement approach in nanoparticles. We are also doing a lot of nanoparticle Raman spectroscopy, and there are many discussions. And this is one approach that we are taking to make analysis consistent with the hypothesis of Nano-ice. So this is one approach.
Thank you very much. Antonella, last question.
Thank you. In support to your observation, I want to tell you that even in the infrared, in vibrational spectroscopy, it's possible to observe 3 different regions. And in the measure support, in vibrational spectroscopy, you can also detect the length of the OH bond. And it's a huge difference between the lowest fraction, the lowest energy fraction, and the highest energy fraction, which support your hypothesis that it's a form of something like ice in liquid water. And the question is, do you think that in the light of your observation, the generally accepted assignment of the broadband of the Raman scattering is misleading, because it is assigned normally to the symmetric and anti-symmetric vibration, and there is another component that is due to the bending, to the second harmonic of the bending. Is it misleading? What's your mind?
Thank you for the question. As a vibrational spectroscopist, I will never do band resolution or broadband into a few components with unknown number. Okay? As you pointed out, even OH stretch region contains symmetric and anti-symmetric. So just resolving those broadband into, say, 4 or 5 symmetric band, it's physically not sound. So we should take it as it is. Spectra letters from molecule. We should not rewrite the letters. Okay.
Thank you very much for your comment. Just let me thank you and say we really need these bands, not in order not to curve fit, because curve fitting is really you stretch the model in 3 or 4 or whatever. But what you start with, I think we need letters exactly. We need assignment, and what I saw in the spectra of Hyper-Raman is so similar to the spectra that we see in infrared.
Yeah, but much stronger in the lower level region.
Yes, so I'm sure we can see the same things in different areas of electromagnetic spectrum from different windows, but we just have to assign them together. Yeah.
And one thing, the selection rule of Hyper-Raman is very close to infrared. So we can get infrared information from Hyper-Raman, but Hyper-Raman can look into living cells. Right. So there might be an advantage of Hyper-Raman.
Yes, looking forward. Really, thank you very much again.
Thank you very much.